standing there, what is the intent of it? Wait, what do you mean you had to blow it off in the water? And that's the thing. Yeah, exactly. Fingers crossed.
Word for local. Third letters that not local.
Word, sorry, say again, word.
For angle B, you have side B,
Yeah, you could use
that's Y Z,
beta with B if you wanted to.
and then you see.
Well, that's why they sometimes use gamma in places C to, yeah, keep it distinct. Well, yeah, essentially a Y, but that's like the Greek letter C in the Greek alphabet, gamma, and then alpha for A. But looks like class has started. This is a really good question. We're getting into these same kind of issues when we do law of sines, law of cosines. And the issue is we have to talk about the angles and the side length simultaneously. So you need symbols where they're definitely distinct. An alpha, beta, B, gamma, and C is how we formalize law of sines. And to keep on that pattern, you could also do A to A. This might break down, right? If you go B to B, those are distinct symbols. And now C to C, that was a problem because depending on your penmanship and how consistent you are, that sometimes looks the same to my eyes as well. So there's a strategy. Put a symbol on the one you mean to be the angle, whether it's a bar, that looks like average, so you could change it to a hat, that's keeping it distinct. Or prime would do it. Any symbol you like that just distincts it from the side length to do the job. Well, welcome back, folks. That was our first question to start us out for today, but other additional questions at the moment? Okay, well, let's run through these announcements. They've been kind of sitting here, so let's get through them. We started section 8.1. The first example is calculating an area of a triangle. We'll have another area formula in 8.2. And we're now on example 2, working on law of sines. If we have time, we'll go into section 8.2, working with the law of cosines. We put it here just as a quick demonstration what that formula looks like. It looks really bad at first, but the more you practice with it, it's actually kind of a natural formula to use, and we'll see why when we get there. But the bigger announcement is in a week away from today, next Tuesday, April 16th, we'll have our third exam over those sections. And this is kind of an awkward exam for me. Let me explain why. When I said exam 3 is going to be open calculator, like the TI-30XA, it's because I was assuming we were on pace for, say, section 8.1 to be on the third exam. It's not going to make it. I feel like throwing 8.1 on the exam is just too much. We're only just starting that content. But I don't want to renege on what I said, so this is still on the table. On exam 3 and the final exam, you are welcome to bring a calculator. That means some of the problems on the real third exam, I might say, be sure to give exact values, since we're going for exact values. We can't just throw everything into the calculator, but you can use a calculator and use it to check your answers as well. It'll be helpful when you practice using the calculator in exam 3, going into the final where we truly need it for these sections above. So that's a little bit weird, but the calculator will be allowed even though there's no direct question that requires it in spirit. As a reminder, the calculators allowed for this course by the math department are the TI-30X2S, the TI-30XA, and we'll be practicing with those in sections 8.1 and 8.2 as we go through the notes. Well, any questions, folks, at the moment with these?
So like we're allowed for the calculator, but what do you mean by like exact values? So do we have to give it in like what you say like up to how many decimal place, or like give with just pi or in radian or something like that?
Saying giving just pi. For example, if you're calculating cosine of maybe it's pi over 6, when it says give exact values, you'd have to give the square root 3 over 2. You could use your calculator as a check on the third exam, but this is what we're going for the results on the third exam.
Okay, thank you.
exact values. Yep, you bet. Thanks for asking about that. Other questions about that at the moment? Okay, well, for the rest of the announcements, we have our third exam. So as you study for the third exam, the major thing you'd want to have pulled up is the exam 3 formula sheet. Yes, this is the actual last sheet of the real third exam. So although everything here is provided, keep in mind that I can't ask a question that's going to use every single identity on this document. It's a timed exam. It's only 50 minutes, so some things I just have to skip around. I'm going to try and grab questions that are representative of these identities, but if I miss out on picking your favorite one, sorry about that. It can't be every question on there. You don't have to print this out, but again, I would pull it up and look at it as you're practicing when you're studying for exam 3, because you want to know where everything is, how to search for it and use those identities, and not having seen that for the first time on the real exam. Well, like before, there's a list of sample problems. If you open up this document, this is just the selected exercises from the real textbook. And I put here in yellow, your homework is probably better for the purpose of studying for the exam. Those are the questions that you've been working on, that you've gotten feedback on. And so those are great to look back over. Any question you might have missed, it's a good one to redo and see where you might have gone wrong. And the lecture notes also qualify as a great source of exam material. You can do, say, for the lecture notes, you go way to the top here, go to the Blink lecture notes, and whether you open up the Word document or the PDF, exam 3 starts in section 7.1. If you open these problems, then you should be able to solve these examples here. And I'd say these are probably just as good as the sample problems that I posted right here. So these are the actual lectures notes that we got through. They're old problems, but again, they're still just as good for the purpose of studying. And let's see, where did I go? Let's get out of there. That was the Blink lecture notes at the very bottom here. And now we are running out of weeks on Moodle. We're right here at the bottom. So that's pretty much how our third exam is going to be. Any last questions, folks, about those announcements, the third exam or otherwise? Okay, well, we're getting really close, running out of weeks. Next week, we'll have a third exam, a normal class on Thursday. On this week, we'll have a normal class on Tuesday, but on Thursday of that week, that's the week right before the final exam. So Thursday, we'll spend all the class just reviewing. I'm going to be posting a lot more material than what you see down here for the sample file exams. I want to post real old exams as well, so you can get a feel for what is a 2-hour exam going to look like. I usually like to give old exams, but sorry, say again? It is a 2-hour final exam. Yeah, just like with college algebra. On our university, all final exams are by default 2 hours long. I have to double check when the time is exactly scheduled, but yeah, if we are scheduled to start right at 7, it'll go to 9. Word of warning though, the registrar has a habit of scheduling these for 8 p.m., going until 10 p.m. That's one of the reasons why I offer to people in the class, if that's a tough time to work around, I can give it at a different time. We'll just coordinate once that happens. But other questions about that so far? Okay, well, now back to section 8.1. We started this section, so let's take a look at what we did just to remind ourselves. The weekends kind of get long. The very first thing we did was we looked at this formula right here, duplicated right down below. It's a nice little sneaky way to calculate the area of a triangle with pre-limited information. If all you know is the angle and the 2 adjacent sides around that angle, then that's the calculation of the area. On this problem, we said the area of this triangle is a half, matching that a half, because side legs 2 and 3 correspond to the interior angle of 30 degrees. We could just throw that in, calculate sine of 30 degrees, and we got 1.5 inches squared. That's kind of cool, but the honest reason of why we like this formula is because it gives us law of sines. On this example too, we used the area formula 3 different times. That allowed us to equate the right-hand side 3 different times. And we ended up with this statement right here, which is the law of sines. we derived it from scratch. But here's a full official statement. Here's where the notes will start. Let's expand this out a little bit more. So for the law of sines, it starts by saying, let's follow the convention. Grab a cursor, there we go, of denoting the angles of a triangle by alpha, beta, gamma, or we could go uppercase P, A, uppercase B, uppercase C if you prefer. Sometimes the book will actually do that in their exercises. The lengths of the corresponding opposite sides are A, B, and C. With all that said, what we need right away is that diagram. So let's place this right here. So it says the angles are alpha, beta, gamma. So I'll go alpha, beta, gamma, that kind of way. It says lengths of the corresponding opposite sides are A, B, and C. So the corresponding side and opposite side of alpha would be the side length A. For beta, the corresponding opposite side would be lowercase b. And for gamma, its corresponding opposite side would be over here, side length C. So that's how it starts out. When you look at these side lengths, A, B, C, they're in the denominators here, here, and here. But this version of the law of sines, if you took the reciprocal of the left side, here it is, then you have to take the reciprocal of all sides. And this is just as good. If we're solving for a side length, typically we do it this way. If we're solving for an angle, we would typically do it this way instead. So it's all just depends on what you want to solve for. But A, B, and C emerge up here on the second version. And you take sine alpha, sine beta, sine gamma on those numerators. Or if you took the reciprocal, same stuff, but it just goes down below. So that's the law of sines. It is a triple-sided equation, the dual triple-sided equation if you took the reciprocal of everything, but you only use two sides at once. Well, we'll practice that right away. Any questions, folks, with the statement of law of sines? Okay, example 2 says solve the triangle. And here's the notice of what we mean by that. When it says solve the triangle, it means we want to find the angle measurement of all angles, interior angles to that triangle. And we also want to find all the side lengths. So this triangle has interior angles 32 degrees, 110 degrees. Any volunteers for how we would get to that angle right there?
Add them together and subtract 180.
Exactly. Over Zoom and in class as well, it's all about the sum of those angles is 180. So you just subtract these two. So when it says solve the triangle, we have to produce this value right here, but that's not the law of sines. That's not the law of cosines. It's just this additional idea. Let's put it here on the page. The sum of interior angles of a triangle is 180 degrees. For the folks who are a fan of radian measurement, you could also call it pi radians. But that means we can start by finding the angle A as A equals 180 degrees. And as folks said, subtract 110. Subtract the other angle, 32 degrees. And we're on our way. Well, let's just treat ourselves to a calculator. Why work so hard? So I got 180 minus 110 minus 32, and we're resulting in 38 degrees altogether. So I'll put a 38 degrees, and that's one step down. If we can find the side length C and the side length B, our work is done. So that's what it's going to come down to. Any questions, folks, with that first step? Okay, now we're using law of sines, and because we're trying to find these unknown side lengths, I would use this version right here. We're solving for A, B, or C, so we might as well keep it in the numerator, saving a step. Now let's decide on which one to go for. It probably doesn't matter. Let's go for maybe B. Sorry, say again? That would work as well. And when you're doing the cross product to solve it, you're just going to throw your variable up into a numerator anyway. So that is just as equivalent. I'll go with this way because it sort of saves a step, but really, in all honesty, just about the same amount of effort. So let me scroll just a touch. If we're going for B right here, you'd probably start by saying B divide by sine B. So that would be this segment of the law of sines. Again, we don't use all three sides of the equation. We just pick two sides that are most relevant. So over here, B is the unknown, but we do know the angle. So now we need to pick something else. I can't go C to lowercase c, because that's an additional unknown. And I can't have two unknown values in one equation. We couldn't solve it. However, this is really powerful. We know an angle and the length of its opposite side, so we're going to use this portion right here. Because we're learning the law of sines, it's a good idea to just write down the formula. Let's call this A. We'll have A over sine A. So that's the statement of a law of sines. I just used these two sections right here. Next step, fill in the information. B is unknown, so it's just going to copy in. Sine B is 110 degrees. A is also known from right here. That one is 38 degrees altogether, or excuse me, 39 centimeters. Not sure where I got that. Oh, that must have been the next thing we're about to do. A is 38 degrees, so we'll have sine 38 degrees down below. So this is law of sines right here. We copied it in just to practice using it because that's a brand new equation. This is the law of sines with values thrown in. And our goal is to solve for this B right here. So we just about have it. All we need to do is clear the denominator. And I often use a cross product, multiplying this way. So last step to get B, we have B equals 39 multiplying sine of 110 degrees divided by sine of 38 degrees. Now this question didn't make it to exam 3. Exam 3 is ending in section 7.5. But had it been, this is why we need a calculator definitely for exam 3. And it's also why we need one for the final exam. I would encourage you for chapter 8. It's a good idea to have a calculator ready to go just so you can practice along with us to see how these are happening. And also, if you have a problem in the calculator, we'll be able to help out somehow, some way. So for me, I'll be using Desmos because it's just really fast. But even in Desmos, click on this button and make sure you're in degree mode if you're giving angles in degree measurement. Usually we don't convert these to radians. We just leave them in degrees on these kinds of problems. On the calculator you're probably using, which would be, say, this one, or the infamous TI-30XA, if you prefer that calculator, make sure you hit this button that says DRG until you see right here that it says DEG, for now you're in degree mode. So if you've got that, you're in good shape. Now, what you would put in the calculator to match up this statement is something along these lines. Let me see what kind of, hey, we could probably use white. That's kind of an unusual choice. In the calculator, this would come in as 39 times sine 110 divided by sine 38. So that's what it would look like in your calculator. Your sine key is this button right here, and no other special operations really. So let's try this together on this calculator. Here's what I would be getting. 39 times sine 110 degrees divided by sine 38 degrees gives me a side length of, let's see, we're rounding to the nearest tenth to keep that level of precision. So this would be 59.5 centimeters. So that's what you should be seeing in your calculator here after hitting enter. 59.5 centimeters altogether. Well, how's that look to folks? Are folks getting about the same value so far? Awesome. So if you're producing that, you're pretty much all set for how these kind of problems are going to go on a final exam, for example, or doing them as homework questions, you're in good shape. So we have 59.5, and if you put it up here, that's not a bad way to convey your results. If you're a fan of boxing out your answers, this is not a bad situation to do that. So I'm gonna box out the answers as well. Because we'll typically for these kinds of problems have a lot of results sort of spread out here and there. So here's one answer, here's the second answer. I'm personally not a fan when I write out my math of boxing out my answers, but I do acknowledge it has its place. And this would be one of those times where we have results kind of floating everywhere. Last thing to get is the side length C, but any questions to this stage? Okay, well, because we're using side length C, I would use this side of the equation. And next, if you use this side, B to sine B, it seems natural because we just found the side length B. I would say don't do it. B is really this right here. And if you use that value, your calculation becomes a little bit more unstable. Use this value. It's probably being rounded too, but it's the most stable value we have to get the most accurate answer. I'm not really very picky on that. I can tell if you use this here and your answer is a little bit off. But the reason I say all that is if you check the back of the book, you'll feel like you did something wrong when your work is algebraically totally correct. It's just a precision issue. So to avoid weird issues with back of the book making you feel like you did something wrong when you are right, I encourage you to use the value that's already been printed here. So that means I'm going to be using the far right-hand side, the far left-hand side, and just connect them together. This one contains the unknown, the C that we're trying to find. So I'm going to start with this. C divided by sine gamma. Oh, I put gamma, but in our problem, let's see here. C goes to uppercase C. That's always kind of a conflict. So let's put in what variables we're actually using. And here's where the earlier comment that Michael made at the start of class becomes relevant. If I put in the C like that, then to my eye, that looks like an uppercase C and lowercase c, but I mean, not really. And you might disagree. That might look just about the same to you. So if you want to tell them apart, sometimes going like this, an extra symbol, a prime, can tell you that's the actual angle, C prime. So side length C over C prime is going to be equal to, take side length A, divide by sine A. So this is a not mandatory step. It's a good one to make whenever you're learning law of sines. I'd encourage you to do this on your homework. Next step is just to fill in the information. I don't know anything about C just yet. But down below, this is going to be sine of, take the opposite side, 32 degrees. This will be set equal to side length A on the right-hand side, which is 39 centimeters. Divide by the sine of the associated angle, 38 degrees. And these equations solve really, really fast. I'm just going to do a halfways cross product, sending this denominator to the opposite side. We then get the side length lowercase c is equal to 39, multiplying sine 32 degrees, divide by sine 38 degrees. And now we're well on our way. Even though, as a final exam question, you're expected to use a calculator, if you put this on paper, I give a humongous amount of partial credit for that right there, highlighted by the red dot on the real final exam. And that way, if you did make a mistake in the calculator, you're not going to lose a lot of credit. So I encourage you, show me a paper trail. This is how I award partial credits on these kinds of problems when you're putting results into the calculator. But we've got to put it in the calculator. So first, I won't do this every time, but we're learning how to use the calculator for the first time. So it just makes sense. What would actually go into the calculator for this one is, looking down here, I would type 39, hit the multiplication symbol, sine 32 degrees. And by the way, in the calculator, does it look like this for multiplication or like that? I honestly don't remember.
The star.
It's a star. Gotcha. Thanks for mentioning that. Let's just make it look as natural as it could look in your real calculator. So 39 times sine 32, divide by sine 38. That's about what it looks like in your calculator. Your calculator is going to scroll, so you might have to use left arrow, right arrow buttons down below to see the whole thing. Make sure you have degree mode in if you're putting in degrees. That's now in Desmos. Let's see what we're going to get on this one. 39 sine 32 divided by sine 38 degrees gives us a measurement of 33.6 centimeters upon rounding. So let's put that in. 33.6 centimeters to the nearest tenth. So there it is. For some reason, I have a psychological need to also fill it in on the triangle. Just looks right. 33.6 centimeters. You don't have to do that. As long as your values are stated somewhere, that's good enough for me. But we did it, folks. We found the angle measurement, the side length, and that side length. Everything else was known, so we really did solve the triangle. Any questions at all with those methods? Oh, they had to work pretty hard, but they did have a decent way to approximate some of this stuff. And the go-to method was, yeah, they did use that sometimes, but the big one was this stuff. This is now getting into some really old math, but I can't even zoom in on that. I don't know if they have a higher resolution image, but back in the day, this is how you calculated a cosine or a logarithm or an exponential. It was from some weird contraption, which was actually pretty accurate. Just about as accurate as this up to a point, the TI-30XA. And this is the whole reason why we rationalize denominators. Square root of 3 in the denominator is just hard to deal with it with the slide rule, but not if you put it in the numerator. So that's some ancient mathematical methods from back in the day. For us, we're using this, but this calculator is using Taylor series, Maclaurin series, like you mentioned, to actually give the approximations. So the calculator is using mathematical methods that are pretty impressive. They all come from Calculus 2, as weird as it is. Well, other questions or comments, folks, with those results? Okay, well, that was so fun. Let's try it again. I want to mention this kind of problem is nice because they produce the diagram for us. We're just looking at it and we can launch right into the computations. But this is more common. Sometimes the example just looks like this. We have some information and it's up to us to produce the diagram. A lot of the actual homework questions are going to look like this. And so exam questions typically look like this as well. I do sometimes on the final exam just print them out so that we can save the trouble. But you can't expect that this is a possibility for a question on the real final. So first thing to do is to build the triangle. That already looks weird because the instructions say, show there's no triangle satisfying that information. In other words, it's impossible to have a triangle at those given side lengths when the interior angle alpha measures 23.1 degrees. To determine that, we're going to build what's an impossible triangle, then algebraically show why it's impossible. It's kind of a fun problem as well. If you're ever being told to do something that can't be done, here's how you can prove that it's really not feasible. First thing is we're going to try to build that triangle. We have a short side length of 2 feet, a longer side length of 6 feet. So I'll kind of just go about like that. Doesn't have to be perfect, but trying to maintain the proportions can help. So 6 feet going this way. Those are all the side lengths we know about on this. But we have an angle measurement of 23.1 degrees. This says alpha. So 23.1 degrees should be opposite of the side length A. It will be right here for alpha. 23.1 degrees goes right there. Because we put B here, we should also call this angle beta. And I need to make this fit a little bit better. I'm just going to drop the unit and call it A equals 2. We know it's in feet. All that's left is going to be a side length C going over here. That one's unknown. And an angle measurement gamma associated with it. So here's the triangle that we need to build. And it doesn't look like a very big deal, but actually this is a major portion of the exercises in both section 8.1, 8.2, is to take that information and step 1, build a diagram. Any questions, folks, about building out those diagrams? Okay, step 2, we're going to use law of sines. And now, again, it's kind of an unusual question. It's telling us that this triangle is impossible. We have to spot the reason. But first, supposing it's a real triangle, we put it down on paper, and now we're going to hit it with the law of sines. Well, what can we do here? To use a law of sines, you need to look for a pair that goes like this. You need a known angle, and you must have the side length of its opposite side. So that's like our anchor point, going here to here. Let's start by saying sine alpha divided by A equals. So we have one side of the law of sines. And now what else? First, observe, you can't do anything with gamma and C. That's two unknowns, so there's just no information to work with on that. So instead, we'll work with beta and side length B, because that's information we actually know. The one unknown is right here, and everything else are known values. So we can have a maximum one unknown quantity whenever we're using that equation. So I'll put here for the next step, sine beta divided by B. So all I've done is written down law of sines based off what information we believe we can use. Now let's fill it in. On left, sine alpha becomes sine 23.1 degrees. It's divided by 2. Over here on the right, beta is the unknown, so we'll just put in sine beta. But side length B was known, that one is the 6 feet. So that goes down below. So that's our equation. And notice what happened. This takes us to section 7.5. It's a trigonometric equation. But you can also think in terms of 6.3. In solving these kinds of trigonometric equations, sometimes it's not a bad idea to use an inverse function. So we'll review that as well when we go through this work. First, this is like the major punchline just to get to this stage, because we're trying to show that there's no triangle satisfying that information. What we're trying to do down there is showing there is no solution for beta. Angle beta cannot be found. It doesn't exist. So somehow, some way, this equation is broken. First thing we should do is let's solve for sine B. Like before, it's about cross products. Multiply both sides by 6, and you get 6 sine 23.1 degrees divided by 2 equals sine beta. Now, next stage, we can say this right here is 3 sine 23.1 degrees equals sine beta. And here's the step where we need to jam this right here into the calculator. So in our good old trusty TI-30 X2S, this is what it would look like. Nothing too major, just a 3. That doesn't look like 3 at all. Let me try again. 3 times sine 23.1 degrees is all you'd have to put in. So now for my calculator that actually works, this would be 3 times sine 23.1 degrees. And I get a measurement of about 1.177. I'll keep the 3 decimal places. So 1.177 equals sine beta. Let's pause right here at that step. There's a problem here for multiple reasons. Any volunteers for one reason why that would be a problem? Exactly, it's left the domain on inverse sine, which goes from -1 up to +1. We're just extended way beyond it. Also, if you try to graph sine beta, the amplitude on the sine function is 1. That means sine goes as high as +1, as low as -1. It'll never hit 1.1, let alone 1.177. That has no solution for that reason. But let's do something even different. Let's say here, let's just rewrite the equation. If sine beta, give it a little bit of space, equals a little bit of space on the right-hand side, 1.177. If there was a solution to this, it could be found by doing this. We're now in section 6.3 using inverse functions. Take sine inverse of the entire left-hand side. If you've done that, you must take sine inverse of the entire right-hand side. On the left-hand side, the reason we invoked the inverse function is because an inverse applied to the original function liberates beta. It's a cancellation, a real cancellation. And now, if that value exists, and we already know it doesn't, the calculator is going to alert us to a problem. So here's what you would put in your calculator. So to find the inverse function, first, it's printed right here, right above sine. So what you have to hit is, let me get a color that shows up well. You have to hit the second key first. This is going to pull up. There we go. Sorry, getting caught up. Hit the second key first. That'll pull up the sine inverse when you hit sine very next. And you should see in your calculator something like this. Sine inverse, like that. Does that look about right to folks so far? Awesome. So now you're calling the inverse function if you go that route. Give it 1.177. Hit enter on that and let me know what you get. I don't think I quite recall, but it doesn't look pretty. Might say something like domain error or something like that. Is that what you're getting?
Yeah.
Awesome. So you should get domain. I don't know if they abbreviate it. Well, I'll just put in domain error. If you ever get a domain error, that's a way the calculator is alerting you something is amiss here. Yeah, if you have a really, really advanced calculator, it has extended the inverse function beyond the real numbers, and its domain is any complex number. So as a complex function, this one can actually be computed. But for us, we're in a land of just real numbers. It's a smaller world out here. This has no solution. So if you get domain error, that's the way the calculator alerts you to that. I will say here, just Xing that out, no solution. So that's what we were trying to achieve. The original question said, let's see if I can zoom out enough, show that there is no triangle satisfying that information. So we built a triangle. If there is one that exists, law of sines would work on it. The law of sines did not work. We cannot achieve a value beta. There's no solution. And so overall, our conclusion is this triangle does not exist. At least not on a two-dimensional piece of paper, like a chalkboard or what you're looking at right here. If you put a triangle like on a beach ball, weird things can happen. The interior angles don't have to sum to 180 degrees. And this might actually work if you put a triangle, just draw it on something that has curvature. But on the plane, this one can never actually exist. Well, any questions, folks, about the solution on this one? Like the complex plane? That's kind of cool stuff. Well, let's take a look for our example 4. Example 4 is going to be our last question of the day, and it's just another law of sines, but it's a more interesting question. This one is actually practical and it's used all the time. Sometimes people call this triangulation. It could be used for all sorts of different things. Here we have something that looks like some kind of cruise liner to radar stations. You want it more exciting, you could imagine there are also have guns or something, and this is like an enemy vessel, who knows? This could be a fun problem. It says here, to determine how far a boat is from the shore, we have two radar stations 500 feet apart, and the angles out to the boat as shown as figure 28. And figure 28 is nice because it tells us everything that's going on, but it's too busy, way, way too busy. What we really want to do is abstract away from this and work here. We have an angle of 70 degrees. Let's call that A because it was called station A. We have an angle here at 60 degrees. We'll call that B because it was referring to station B. That's unfortunate. I don't want to call this one a boat. We'll just call it C. Our boat is now C. And they told us the two radar stations are 500 feet apart. They gave us lowercase c. Let's put a prime there to say it's uppercase. This one is at 500 feet. So we'll do all of our work right over here. Let's see what the questions are going to be. Determine the distance from the boat. Let me try again. Determine the distance of the boat from station A. So C is the boat, here's station A. We need to find side length B. I'll put a question mark there to start. And the distance from the boat to the shore. That was a little bit more annoying because they're saying the boat, that's up here, the shore is down here. We have to now drop down a perpendicular, which means we have produced 90 degrees on this triangle. And this would be a side length, I'll call it H because it looks like a height of the triangle. And that's the two things we were looking for. So we have our two questions we're trying to ask. We have the overall figure we're going to work on. Sure, we're working with boats and satellite stations that are triangulating, but the mathematics is probably a little bit easier to actually see over here. So we'll do it in this diagram. Now let's determine what is the easiest thing to even go for. Let's go for this part. Determine the distance from the boat from station A. So here's station A. Here's the boat. They're saying determine that distance right here. And that's kind of nice because we know that angle measurement for B. It's at 60 degrees. So we can start by saying B divide by sine 60 degrees. And we have 1/2 of the law of sines. We can get the right stuff over here. Our work is going to be just about done. So let's see what we have. We have a angle measurement of 70 right here, but we don't actually know a side length that goes here whatsoever. That means I wouldn't want to use angle A. That's unfortunate. So we'll try again on something else. For angle C, we do know that value, 500 feet, and we can produce that angle. Anyone see what that angle ought to be? 50 degrees, good call. It's back to thinking in these terms. Oops, I clicked away my calculator. We're just going to say the sum of the interior angles of a triangle is 180 degrees. So subtract off 70. Subtract off the other 60 degrees that was provided, and it'll be 50 degrees right here. So let's put in our diagram that this measurement is 50 degrees. So next, we'll use the side length 500 feet, divide by sine of the angle opposite 50 degrees up here. And notice we just about have B. We'll clear the denominator, throw everything to the calculator, and we'll be well on our way with this one. Any questions to that stage so far? Okay, so let's multiply this way, a half cross product, and say that B is now 500 times sine of 60 degrees, divide by sine of 50 degrees. Let's throw this into the calculator. Let me know if you're getting something different, and we'll try to reverse engineer what could have gone wrong. For this altogether, I'm getting 500 times sine 60 degrees divided by sine 50 degrees, and it's going to come out at about, they said round to the nearest whole foot. So it'd be 565 feet altogether. And you know what? That looks like it's in the right ballpark. The distance between the stations was 500 feet. Even though this is not guaranteed to be drawn to scale, it does seem about right that this would be in the neighborhood of about 500-ish feet. A little bit longer going this way to this way than this way, in other words. So going back here, let's fill this in and say it's 565. The reciprocal of sine, that would be a cosecant. So we've got half the answer down. We determined the distance from the boat to station A, but it also says, and the distance from the boat to the shore. So here's the boat, there's the shore. They want to know the side length h. So let's highlight that as a reminder. Here's the portion we're working on. Side length h is a little bit awkward because it's the height, the altitude of the triangle. This diagram is now way, way too busy for us. We need to extrapolate or abstract away from it as well. So I'm going to take this diagram. We only want a segment of it, so I'll put that segment in blue just to highlight it. We're going to take this portion. That's too big. Let me try again. We're going to take this portion like that. Here it is. And do our work right here. So we still have 70 degrees going this way. That's starting to look weird. Let me drop the size on this. There we go. So 70 degrees still going this way. That's a perpendicular, so it's 90 degrees. And now we need this measurement. It's no longer 50 degrees because we've taken away some of that rotation, but just use the same trick as before. The sum of the interior angles of the triangle is still 180 degrees, even if it's a right triangle. So here you could take away 70. That's 90 degrees, so you're taking away 90. And you're resulting in just 20 degrees right up here. Maybe a better way to say it is, in a right triangle, the other two angles that are not the 90-degree measurement sum to 90 degrees. So if you saw 70 there, that's got to be 20. That's a great way to think about it as well. We inherit a couple things. We know that the side length, the hypotenuse, is 565 feet. And what else do we know? We don't actually know that measurement because the whole length here to here is 500 feet. And I don't know where that would be proportionally. So that's okay if we don't know it. But what we want to know is h. So the moment you find h, work is done. We'll know the distance from the boat to the shore. Awesome. Which approach did you take on this? Yeah, that's personally what I would do right away. The moment we're dealing with a right triangle and we just want one side length, SOHCAHTOA is going to do the job. We're based off of this angle, and opposite of this angle is h. That means you probably want to use this part of SOHCAHTOA. That's a weird color to use. Let's use green instead. If you use this part of the SOHCAHTOA mnemonic, then you will automatically involve h and the hypotenuse. So sine of, let me put it where it's possibly going to fit if we solve it entirely. I realize I'm running out of space on this finally. Well, in this case, I'm just using the SOHCAHTOA formula. So yeah, it would place the unknown right here, right up into the numerator, h. But even if you did something else and say use cosecant, h is in the denominator, that's okay. Just take a cross product and you'll still get the right result. This will be divided by h, which is the hypotenuse, 565 feet. And in this way, I still have to use a cross product. I'm going to multiply 565 this way. And this will tell us H equals 565 times sine of 70 degrees. Let's see what that comes out to. We get something like 1,000,000 feet. We know we're way off. If we get like 2 feet, that's way, way off as well. So here's the moment of truth. 565 feet times sine at 70 degrees to the nearest foot is 531 feet. And you know what? That looks believable. That's well within the ballpark of what we would expect. Oh, gotcha. Awesome. You said 530, what was it again?
531.
Gotcha. I took mine and got 0.92. We're pretty close. I only rounded to 531 feet because, well, they asked us to, but I'm not too picky on those kinds of instructions if you gave me something more precise. But we did it, folks. This is a pretty honest application of what you'd want to use trigonometry for. This kind of stuff is used every single day for triangulation. Any questions at all working through these methods? Okay, well, this is a good stopping point. I notice I'm running over by a minute. Sorry about that. When we return on Thursday's class, I'll be happy to take any questions you have with the upcoming exam 3, which is next Tuesday. After taking questions, we'll be moving over to law of cosines. Well, have a great night, folks. Drive safe if you're in class or in Zoom and you still have to drive. And I'll see you all in Thursday's class.
Thank you.
Yeah, that's kind of cool. It's amazing that radians is pretty pervasive. So you're saying even if you put in degrees, it's going to convert it for you. That's kind of neat. Mhm.